My name is Hal. Good afternoon, everyone. And this is my colleague, Wang. And it's great to be back because actually I was here 2 years ago giving a speech about how we use Flink streaming processing with rule engine to do threat detections. And today we got even better because we are bringing you a brand new machine learning platform that leverages Flink SQL and machine learning algorithms. So let's just get started. So this is the agenda for today's topic. So I'm going to talk about four things. First, I'm going to give you a quick introduction about what UEBA is and why it demands for machine learning capabilities. And then I'm going to walk you through a typical machine learning engineering pipeline. And then we're going to the fun part, why we choose Flink SQL and how we use it. And finally, my colleague is going to give you a live demo, so that's the showtime. Okay, so what is UEBA? So the idea of UEBA is it's user entity behavior analytics. It's invented by Gartner in around 2014, and when the big companies and enterprises were concerned about insider threats and data leakage or even business espionage. So over the years, UEBA has been a hot topic in the cybersecurity realm. So that's why we do business. So here I've listed some categories of threats that UEBA is meant to detect. So in the blue circles are the main categories. First, we have this account security. So is this account compromised? Or is this privileged account has been abused? Or is this account shareable? Multiple users are using the same account? So that's about account security. So, and then we mostly focused on the insider threats. So for insider threats, we have malicious users. Maybe they could be hackers from outside of the company, or they could be employees in the company. And also we have ignorant employees. They just don't know the rules of the company, so they made mistakes. And third, we have data leakage. That's what DLP is for. And UEBA is built on top of DLP. It can just narrow down the threats that has been generated by DLP. And finally, we have business fraud. So in terms of business fraud, an example would be that every time a online shopping website is giving out coupons or giving out promotions, there will be bots that's crawling the website to get the company ripped off. So that's what we are interested in with this UEBA technology. So why UEBA needs machine learning capabilities? Those are from our experience with our customers. So firstly, statistical analytics may not be enough for certain use cases. Actually, for most of the use cases, those statistical analytics works, but it just generates too much false positives. And the second, we need machine learning to get deeper insight on long-term data. So because the customers can provide you a month amount of data or even years of data. So what you do with this overwhelming data, because you have a vast amount of data in your hand, but you don't know how to get started. So that's what machine learning kicked in, specifically unsupervised machine learning kicked in. And then third, we have customized scenarios that needs data scientist specialty. So that's the case in our experience. So for most of our customers, they just have this bizarre or weird use case that needs to be tackled. So we need algorithm experts to do the work. So finally, we have to, for UEBA, to make a good UEBA system, you need to connect dots between different data sources, between different threats to know the user's behavior in the time fashion, because human beings are complicated, right? So, but there are some challenges on machine learning. Quick poll here. So how many of you guys are confident to say that you are a machine learning expert? Raise your hand. So no one. Oh, just one. OK. And how many of you have tried machine learning 101 just to load the files and train the models and make a prediction, and you think you're good, that you sit for coffee? Just a few. OK, about half. OK. So That's right. So that's the thing. Most of us just dabble in machine learning. We just use call the APIs that's in Python or like PyTorch or something, some other things. But we don't have the ability to tune the machine learning models or even to tweak the algorithms. So and also, if we use basic machine learning functions with like default parameters, it's not a once and for all solution because it's a case-by-case situation. This machine learning algorithm may fit into this use case, but if you put it into another use case, it doesn't work. You need to like fine-tune this parameters. You may need to do tons of iterations to get the result you are satisfied with. So that's the problem with the machine learning. So the first three are just the intrinsic characteristics of machine learning problems. And the last three, the number 4, number 5, and number 6, are all about collaborations. Because for an technology company, you'll have software engineers and you'll have like algorithm experts. So they need to like collaborate at some level because you are building a product, not just a snippet of code that can run here but not there. So if you are trying to sell your product, you need to find a way to make the co-work of these two kind of people easily. So that's why we need a machine learning feature model management to ease the work between software engineers and data scientists. So that's about the challenge we are facing right now. A quick recap of the machine learning pipeline in general. So first, you need to take care of your data. You need to make sure your data is in good quality. And then you can do feature engineering. And let's admit, the feature engineering is difficult because you don't know what features you need. And you don't know how much feature should be calculated and how much is good. And then once you're ready with your feature, you can put them into a model and train the model. And you may do tons of iterations of models to get the right one. And after that, you can do model evaluations for every model you get in each iteration. So after that, you're good with the model, and you can just apply your model to the other data you have split it out to do the predictions. And if the prediction rate is higher, the accuracy is good, and then you can just publish this model for your future data. And for UEBA product, we are interested in the final threats incident. So we just use the first 5 steps to generate the incidents that can be shown to the customers. So this is the whole process we are using right now. So here's an example from a customer of ours. It's an airline customer. So it's a real case. So this is a business fraud case. So here we have this client. It's making requests to this web API. It's a business API. Actually, in this case, it's a ticket price query API. So it just constantly requests this API, and we just generate some features like request frequency, request window count like by second, by minute, or by hours. And also we have this response status code, count, and some other stuff. So with these features, we just put them into an unsupervised clustering algorithm because we don't know what this data look like because we don't have any labels there. So we just do some basic clustering. So here we have 2 graph here, 2 scattered plot here. And when we dive into all the dots, we found out that the cluster F2 is actually interesting because it says that something is crawling the website constantly and in the constant interval, like every 2 seconds, and then like every second, and then wait like 5 seconds, and then every second. So once you find out this kind of interesting thing, you can label them, and then use the labeled data to do a supervised modeling with XGBoost or some other algorithms to get the binary decision tree here. So that's how we do things with a typical machine learning process. So this is a real case. But in this case, we put a lot human effort in it because none of these steps are automatic by then. So we were thinking about how can we just ease the process? How can we just reduce the cost? Because human are costly, time are costly. So that's how we came up with this AutoML idea. So one thing worth mentioning is the feature engineering. So how we do feature engineering in our company. So here is an example of a typical user logon scenario. So we can calculate the daily logon count or the daily log account by device, or we can generate the client-server connection patterns and so much other stuff. But there will be problems with feature engineering. Like I said, it's hard to choose the right one or even the good one, the good features, because you don't know. Usually the experience is that you just calculate as much feature as you can to see the result, but it'll generate too much like false positive because the data quality is not that good. So again, data quality is the key to every machine learning steps afterward. So, and then the second is time validity of feature, and sometimes even you need to do real-time features, especially in like consuming products like food delivery apps or transportation apps or map apps. So that requires real-time features. And then finally, it's again the data quality. Sometimes you may train your data to get a model you're satisfied with, but when you apply this this model to other data, it just doesn't turn good because the data is skewed. So you have to first make sure your data is like evenly distributed. So that's the basic stuff of feature engineering. And for feature engineering, we also have to find a way to store all this data, all these features. So we have two modes of feature store: batch mode and real-time mode. So for batch mode, it's for long-term data. So if we have let's say a month or a year amount of data, then you can just do some basic statistical data aggregations to get the features. For example, how many users has been logged on to the system today, per day, or per month? Is there any new account that has been activated now, but that's been dormant for like a month? So that's the batch features. So for batch features, we can also do bulk access to all those features. So you can just call an API to get those features. And also the batch feature is only inserted into the database, not updated. For real-time features, like the one I've said for like the transportation apps, then you need to do, what you need to do is that you need to keep key by those features by timestamps, because time is the key thing here because it's real time. And then you need to find a business specific dimension. For example, it could be the device ID or the user ID or the IP addresses or the like even geolocations. So that's the dimension. And also you can store those features that's been calculated on the fly in the memory for like time-sensitive use cases. And then after you serve this time, you can persist it into the timescale DB, which is a Postgres extension. The reason we choose timescale DB is that intrinsically it has a timestamp as the key. So it just put data in a chunk. It just put data in a chunk of time ranges. So every chunk has a data that falls into this time range. So when you do search, when you do update, it'll be very quick. So that's why we choose it. And so it can be accessed with the time. So every time you want to search for some data, you have to specify the time frame, so it can get you the data very quickly. Okay, so finally we get to the the most important part. So why we choose Flink Circle and how we use it. So far we've been just talking about how much pain we are in when we're trying to do a machine learning processing, even a simple one, and it just requires so much knowledge, expert knowledge. So why we choose Flink is that we want to build this machine learning platform that can ease the whole process. At least it can just narrow the chasm of between the data scientist and the software engineer. So why Flink? That's the first question. So the answer is simple. Because Flink has been growing aggressively over the years, and it's getting better and better. And Circle, let's say, it's always great. So that's why we choose Flink. So that's one word to say it. But I've listed some key notes here to demonstrate why we use Flink. So first, it's a streaming circle in nature. So everything in Flink is streaming, even the circle. A circle is just a way of calling the APIs, but everything is happening streamingly underneath. So, and the second, Flink also supports like multiple data sources, say like message queue like Kafka and active queue, or some text files. Excuse me, text files, CSVs, or HBase, or sockets. And then Circle, like I said, is the most popular language for both software engineers and data scientists. That's what we like, because software engineers can do the data scientist can do what data scientists do, and vice versa. So we want to find a way to just connect the two parts, the two parties. So we choose Circle to do the stuff. And then Flink Circle supports dynamic result updates, and also Flink Circle supports CEP. And CEP is what we depend on strongly, because we are doing user behavior analytics. That's like something happens at this time, and then what happens after that during a time of range. So that's that's the typical CEP use case. So we want that. Finally, we have this highly customizable UDFs to meet specific business requirements. So UDFs, so that's the best thing. I think that's the best thing among all of this, because you can just, because UDFs means freedom. You can just define UDFs of your interest. You can say it's just a simple function, like a fill tile function, or that's equivalent to the where statement in Circle, or you can define like machine learning algorithms as an UDF, then you can just call it in the Flink Circle. So that's the beauty of it. Okay. Here I present you the HQL hand-side query language. It's actually a patent owned by our company. For those who are familiar with Splunk SQL, you'll get a handle of it very quickly, because it's similar to Splunk SQL. So it's a Circle-like query language, and it's also with Linux command pipeline format. So you can type something, type the first command, and then you can give a like this sign, and then you can type another one. So the result will be transported through the pipeline. So, and then it covers basic filter predicates, like I said, where if one condition meets, then what, if else what. And then also we covers like some classic machine learning algorithms like XGBoost, like SVM or K-means. Those are all built in our systems. Also, this will be HQL will be every statement you've typed into the SQL interface will be parsed into Flink jobs to run. So basically, it'll parse into Java code, and then we compile this Java code to Flink jobs, and then we run it on Flink clusters. That's the whole process. So finally, we have this with HQL. You don't have to know details of Flink Circle APIs. You don't have to write Java code or Scala code. You just need the basic knowledge of Circle. Then you can use the unified APIs on the higher level. So finally, with this HQL interface, you can build, test, tune, apply, and see the results of your machine learning models just in one place. So Here is a snapshot of the interface of SQL. So for the basic filters here, so this file dash source means that we are reading files from this file, and then we specify the type, it's ORC. The reason we are using ORC is that Flink is supporting ORC natively. And also we support JSON, Parquet files. But in my opinion, Parquet files may be a better choice because it has a higher compression rate. So for the same amount of data, Parquet file could be smaller, much smaller. So, and in the second paragraph here, we have a filter keyword here. So what it does is that just filter everything that has the Windows event ID not equal to 3. So this orange keyword here are just basic EDFs we created using the Flink circle and to just help users to ease the work. So this is how it looks like. And then we also support like machine learning algorithms. So here, as you can see, that if you type into this AutoML keyword with a dot, it'll just pop up all this information that it supports. It'll give you an information of every algorithms, what arguments it takes, and what it does. It has some usage descriptions here. So here, the example is that we score this model. Just we want to try we want to train the model and score them to see which model is better. So we have all this. This is the table we are using. So this is the input, the data input. And then we have all these features here. So with this feature keyword here, we have like device count per day or device unique city count per day or like device unique IP count per day. So those are the features we're using for this case. And then we save this model, save the result to a file. So this is a visualization for the whole process. It shows you that the accuracy in the histogram. So the green one is an accuracy, and the blue one is another parameter that's typical in those algorithms. So this is how we do things with SQL to do machine learning process. So come back to the feature combination example. So if you have multiple features, you may want to just join them, combine them to like a wider table view. So how you do that is that you just call this AutoML.combine feature here, and you specify your features. Also, you have to specify how to join them, because if you want to join them by user ID or by IP addresses or by timestamp or by devices IP, you have to specify that, and then it'll give you this result. So you can see that in the first paragraph, we just read all the data here, and then we combine all the features. It'll give you 3 extra columns here showing the features from the database. So that's how we do feature join here. Finally, how we just I've mentioned that every statement in SQL will be parsed into Java code and compiled and run on Flink's cluster. But how we do it, how we just make this thing look so simple, is that, excuse me. Here, as you can see, we have a Scala function here. This is an UDF. It's called combine features, and you have to specify all those arguments in it. So the first one, paragraph ID. The paragraph ID corresponds to all those 2 paragraphs. So because in SQL, it's run in an orderly fashion. So every paragraph depends. The input of every paragraph depends on the output of the previous paragraph. For example, here, so you read all the data in the first paragraph, and then it'll take all this the results and combine the features in the second paragraph. So that's an orderly fashion. So you have to specify the paragraph ID here, and then you have to specify the features you need to combine, and also the group IDs. Group IDs means dimension IDs. in this case, it's device ID, IP addresses, or cities. So that's the group field. Also, you need to specify the time field, what the time field is called, like is it called timestamp or occur time or event time? So you have to specify that. And the rest of it are just some metadata for your feature store. Where is your feature store? How to access the IP address, the port, and such. So with all those arguments, the real thing, the real magic happens here. So we have this async function. We are using like Google's gRPC to do this async function, feature function here. So it'll get a function from your database, and then it'll just do some transformation to transform those features into rows of data. So the result stream will be rows of data, and then we transform these rows of data into a Flink table here. So that's the basic way of doing the UDF, to define the UDFs in our HQL. So finally, we get to the final part of our system, the automatic machine learning platform. So here you can see that we have, on the left-hand side, we have a menu bar here. So we have like a data source. So currently, we are supporting like Elastic's data source or like text file data source. And then we have those data processing functionalities. For example, you can split the data, or you can filter the data. So those are just basic ETLs. And then we have supplied those algorithms like XGBoost, those classic ones, k-means, everything you need for a basic starter. And then finally, we have the operations for models. We can score the model, can save the model, and you can apply the model. So all those are the functions that you need to do all this AutoML processing. So on the right-hand side, the main part, we have a palette here. So in this palette, you can just drag and drop, actually. So you can just drag one node at a time and just put it in the palette here. And then you can just connect dots to between every node. So it'll just take out all the graph. It'll just read the graph, and then it'll just run the whole process to get the result for you. So that's just a snapshot for this. So so my speech is here. So, and I'm gonna hand over to my colleague Wei to do the demo, the live demo. So, just breathe and show time.
Yeah, I'm very glad to be here to show you how to build a machine learning job in automatic machine learning. Firstly, we create a graph named login model example we have already created. So we clicking on on the left, we can see all of the operators we supported here. And so we drag in the operator to the panel to build the pipeline to build the job here. Firstly, we specify a file data source. Then we input the file path. And we select the column we will read. In this, we select 5 columns named IP, device, CT, log ID, and row time. As we mentioned before, we will combine features from the feature store. In this demo, we'll combine 3 features from the feature store. Sorry. The first feature named device unique IP 1 day represents how many distinct IP addresses a device log on per day. And the second named device unique CT 1 day, it represents how many distinct CTs a device log in per day. And the third one represents how many times a device log in per day. Most of the time, we are dealing with unlabeled data. So the usual practice is to perform unsupervised clustering, to generate the label, and then train supervisor classification models. So we choose a clustering node here. We need train data to train a supervised model, and we also need test data to validate the models. So we should split data to train data and test data. And then train data are used to train models. And test data score the models. At last, we will save our models. After we configure all of our loads, we just run our graph. It will take a few minutes, so I will open another graph with the same processing to see the result. For this histogram, it shows the matrix of all the model we have trained. And we can simply choose the best model according to the histogram. And for this shows for this cluster scatter plot, it shows the result of the clustering. The clustering algorithm divides data into two clustering named C0 and C1. If we have choose our best model, so we can use our model to do a prediction. We can also create a new graph to do the prediction. First, we do the data source, and then we also select the same column we need, and do the same feature store. And the last step, we will use the model we trained to do the prediction. We select the model we choose and confirm and run the graph. It will take a while. Yes. As you can see in the last column, it's the label our model predict. As we mentioned before, our AutoML is built based on the SQL platform. So when we run our AutoML job, it will generate a SQL notebook. You can see here. In the left is the schema and the table information. And it looks like the Python Jupyter. You can run every paragraph. And each paragraph is represent the single node in the AutoML graph. Okay, that's all the demo.
All right, so that's basically how we do things with. Okay, the mic's not working. So that's basically how we do things with AutoML and with and HQL. So AutoML is built based on HQL. So deep down on the lower level, everything is running in Flink jobs. So that's the whole idea. So that's the presentation. So any questions?
What kind of models and frameworks do you use behind this AutoML?
Okay, so for this, like the language grammar, we are using Antler 4. So Antler4 is a tool that you use to define your own language grammars. So with that, you can define like circles or Java, so you can define everything actually. Then it'll just, Antler4 will just take care of the other thing. It'll parse your grammar file into like a parser. Then if you write like a statement that's not illegal, it'll just pop out those error informations. So that's basically how we created HQL. And apart from that, everything in this HQL is in the format of circle, and as you can see there. And actually here in the future works, I have something mentioned here. So here we actually are thinking of transforming circle-based language grammar to Python ones, because as you've seen before, everything in here are like the features here. So they are connected with commas, like you just spread out all these features, but it's like from the user experience level, it's not very easy to use. So we are trying to translate this into a Python grammar, so where you can have brackets from two sides. So that's kind of looks like a function for to the data scientist. So that's why we are thinking about this. And then if we're using this one, and we can do better integration with Python machine learning toolkit that's out there, because let's face it, Java's not doing a very good job for the machine learning stuff. And finally, the way of doing it, we are thinking is that we want to run Apache Beam on Flink, so that we can just wrap Java code or Python code or other languages code to run on Flink cluster. So, and also for this built-in algorithms that's out there, you have to be able to tune every parameters. So we are still working on a better user experience interface. So that's what we want to do. So the final one is a comprehensive workflow management system. So where you can just monitor your models and just publish your models, run your models, or stop your models, and see every detailed information of your model. So that could be very difficult to a system to implement, but we need that very much. Yeah, so that's pretty much the work we need to work on later days. Yeah. Any questions?
So the algorithms you wrote, are they using SQL as well, or they are actually written in like data stream?
They are implemented in Java. So we have our own implementations in Java. So that's equivalent to the Python implementations. So that's why we only support like a limited amount of algorithm right now.
Okay, but when you do the training, are you also do the training in Flink?
Yes.
Okay. So, and which API are you using to do that, to write the algorithm, basically?
Okay. Let's get back to the... So here?
Yes.
So this is the attributes version of UDFs we created for Flink Circle to do the stuff. So we basically we have the implementation in Java, and then we just wrap it into Flink Circle or UDF, and then just put it into the HQL.
Is this distributed?
No, it's actually it's just a prototype, so it's not a distributed system.
Okay, I see. So is there any plan to make it distributed?
Yes, yes, because distributed systems are in demand.
Okay. Okay, cool. Thanks.
Yeah, no problem.
So we have time for 2 more questions. Anyone? Okay, I would say then we should thank the speakers.
Thank you all. It's a pleasure.